In this video, I'll talk about the Arrhenius equation. The Arrhenius equation is possibly the most important equation in chemical kinetics. This equation shows that the reaction rate constant K depends on the energy barrier or activation energy and the reaction temperature. The equation is this. Make sure you can remember this equation. Reaction rate constant K is equal to a pre-exponential constant A times e to the power of negative activation energy over RT. By just looking at this equation, if you have a huge activation energy, you are looking at e to the power of negative very large number. So this is going to be 1 over e to the power of large number. 1 over a large number is going to be a small number. You have a small k and a slow reaction rate in that case. But what if you also have a very high reaction temperature? So if this temperature is high, very high, and this RT is comparable with the activation energy, and then this fraction is not so big, and then e to the power of negative activation energy over RT is not going to be too small, and then you have a decent reaction rate constant and a fairly fast reaction rate. Again, just a review, the reaction rate for a second order reaction is this: R equals K times the concentration of A and the concentration of B, assuming A and B are the two reactants. A and B will collide with the right orientation with sufficient amount of energy to overcome the barrier, and then we'll get the product. So again, just to repeat this very important factor, the reaction energy barrier is very important. The larger the energy barrier, the smaller the reaction rate constant. So what about this A? A is the pre-exponential factor. You can call that effective collisional frequency. The reason is, if A and B collide, they may or may not react even if they have enough energy, because sometimes the orientation is not right. Again, for H2 to react with Cl2 to produce two HCl molecules, somehow you need the orientation that allows one H to be close to one chlorine and the second H to be close to the second chlorine. And then it's possible for the collision to produce two HCl molecules, right? So we need the orientation factor. It's usually much smaller than 1. So typically this P, this orientation factor, is between 1% to 10%. What about Z? Z is the collisional frequency, assuming each reactant has a concentration of 1 molar. So again, Z is just how fast those molecules collide with each other. And then this R is expanded. This reaction rate is expanded to be, again, this is K times A times B, but this K, the reaction rate constant, is P times Z times this exponential function of negative activation energy over RT. All right, so now you know the few factors that does affect the reaction rate other than the concentrations of A and B. So you have this factor, this is the energy factor. You need high enough temperature. You want a high temperature to have a larger exponential function here because of this negative sign. Okay, pay attention to this negative sign. If you have a infinitely high temperature, plug it in, it's infinity here, and then we have E sub A over infinity, that's 0, and e to the power of negative 0 is 1. You get a value of 1 here. What if you have a really low temperature? Let's say temperature is close to 0K, and then you have e to the power of negative infinity. E to the power of negative infinity is close to 0, and then you have nearly 0 reaction rate constant. So again, this is very important factor. And then collisional frequency Z. So really, this Z is the collisional frequency, assuming A and B are 1 molar. What if A and B are not 1 molar? You just need to plug in the actual values of the concentrations of A and B. Alright, so if they are like 2 molars each, and then the reaction rate is actually 4 times higher than just 1 molar each. Orientation factor P. Again, P is a small number. It's usually between 1% to 10% because, again, not all collisions are effective collisions. For A and B to react, first they need to collide, and also they need to have enough energy to overcome the activation energy. But then there's a third factor, the orientation of the collision. Again, you need the right angles for this reaction to take place. So at least 3 factors here besides the concentration of A and B. I'm talking about P factor, Z factor, and then over here this exponential function is very important. It depends on the temperature. The higher the temperature, the higher the reaction rate constant. All right, just to show you this important Arrhenius equation again, the reaction rate constant equals this pre-exponential factor A times exponential function. The exponential function is e to the power of negative e sub A over RT. So really, by looking at this equation, somehow if we have some experimental data of reaction rate constants at different temperatures, we can determine the activation energy. But how? So first, we need to transform this equation by taking the logarithm of both sides. So Ln(k) is Ln(a) minus e sub A over RT. Okay, this is because the logarithm of e to the power of negative EA over RT is negative EA over RT. Logarithm and this exponential are opposite operations. So if you take logarithm of e to the power of anything, the result is that anything. Alright, so we're talking about logarithm of e to the power of this negative e sub A over RT, so that's why we get negative e sub A over RT here. Alright, so why do we need to do this? You probably realized that this Ln(k) is a linear function of 1 over t now. So again, if you make a Excel graph of Ln(k) in the y-axis, 1 over t as the x-axis, it's going to be linear. The slope is going to be negative e sub A over r. That's the slope. The intercept is going to be Ln(a). That's the intercept. So if you have experimental data, you have the reaction rate constants K at different temperatures. All you need to do is you need to convert K to Ln(k). Convert temperature to 1 over temperature. And make an Excel graph, do linear regression. You get the slope. The slope is negative e sub A over r. That's the slope. Therefore, if you have the slope, multiply that slope by negative r. The result is the activation energy. Alright, so very important. Ln(k) is your vertical axis, 1 over t is your horizontal axis. So now let's work on a real practice problem over here. Let's say, oh, by the way, I want to mention this, the slope of this, you need to use the slope of Ln(k) versus the slope of Ln(k) versus 1 over temperature. Okay, so you get the slope of this graph, and then the slope is actually negative e sub A over r. Therefore, you have to multiply the slope by negative r to get the activation energy. Alright, so practice problem, assuming we have the reaction rate constant at 2 different temperatures. K is 1.0 at 280 K. K is 10 per second at 300 K. So we're going to calculate the energy barrier of the reaction. So again, we're going to look at this equation. We're going to make a graph, Excel graph, which should be Ln(k) over 1 over t. And then we get the slope. And then multiply this slope by negative r, we get e sub A. So let me use the Excel here. So we have K, we have temperature, right? K is 1.0 per second. So we need to put the unit here. Okay, and then it's 10 at 300K. It's 1 at 280K. So you can see if you increase the temperature, the reactant rate constant increases. So we can't just make a graph out of this raw data. We need to do some treatment. So first, 1 over T is going to be our horizontal axis. So I put it on the left. And L and K is going to be our vertical axis. So I'm going to put it on the right. So this is horizontal, this is vertical. So I'm going to use the equation 1 over temperature here. And I'll drag it down. Okay, I got two temperatures. And they're reciprocals. L and K. I'm going to do negative, L and K equals L and K. Okay, over here. Okay, and then we drag it down. We got the Y values. This is X values. I'm going to highlight these two columns. I'm going to do insert. I'm going to click this scatter and then get a graph. This graph looks a bit too big. So I'm going to just add a trend line here. Display equation. Display this. There's a problem here. Okay, there's a problem with this graph. I'm going to select data. Okay, what I would do is I will select this data. Nope. Forget about the graph. I think there's something wrong with the graph. What I would do is I'm going to get the slope right away using the slope function. Just type equals slope. Okay, and then you will see the syntax here. Slope, no y values, no x values. So I need my y values here, comma, and I'm pressing the control button. Okay, so that's the slope. Okay, that's the slope. If you want to get the intercept, equals intercept. And then again, y value, comma, x value. All right, you get the intercept. All right, that's easy. And then what if we have 3 data points? Okay, if we have 3 data points, we just enter, maybe this K is 100. All right, at let's say 320K. Okay, and then what we need to do is we just need to drag it down. All right, and for this slope, we're gonna just include more data point. That's gonna be the slope. So you got the slope right here. What about intercept? Again, intercept, you just need to drag it down. Or you can just change this E3 to E4. Okay, E4. All right. So E2 to E4. That's your Y value, 3 of them. D2 to D4, 3 X values. Okay, now you get the intercept. All right, and also let's say if I delete this number, you will get back the original slope and intercept. I'm gonna keep it here in case you are interested. Okay, I didn't save it, but that's fine. So this is the intercept. This is the intercept. This is slope. But remember, the activation energy is not the slope. It's negative R. So this is the gas constant times the slope. All right, it's negative R times the slope. So indeed, this one is the activation energy. It's in joule per mole in the SI unit. The reason I know it's the SI unit is because I'm using Kelvin, I'm using second. Those are SI units. And when I do this multiply by negative R, I intentionally used the value of R, the gas constant, with SI unit. Again, with the SI unit, the R is 8.31446 joule per mole K. So anyway, I got this activation energy right here. Let's get back to the document. Again, we know the slope of lnk versus 1 over t. This is a linear plot. So we get the slope, and then multiply by negative r, we get E sub a. And we know E sub a is from the calculation, it's 80,000 joule per mole. Okay, 80,000 joule per mole. Now let's get back to the document. I'm going to show you a different way to do the calculation without using an Excel spreadsheet. I'm going to do this. So I'm going to copy this same Arrhenius equation twice here. Okay, in the logarithm form. And then I'm using the same equation twice for temperature 1 and temperature 2. Okay, at temperature 1 I have K1, at temperature 2 I have K2. And now I'm going to take the difference between these two equations. I'm going to use the second equation minus the first equation. How do we do that? Well, very simple. I'm going to use the left-hand side here minus the left-hand side. I'm going to use the right-hand side minus right-hand side. So on the left-hand side, you get this. On the right-hand side, where does this a go? We have ln(a) minus ln(a), it disappears. And then I have this negative E sub a over r times 1 over t2 minus negative E sub a over r times 1 over t1. So there's a common factor. Negative E sub a over r, that's my common factor here. And then I have 1 over t2 minus 1 over t1. Alright, so really in the end it's just this equation. ln k2 minus ln k1 is ln of k2 over k1. That's logarithm operation. Again, ln x minus ln y is ln x over y. ln x plus ln y is ln x times y. Remember that. So now we have this ln 10 over 1 here. It's a logarithm of 10. It's roughly 2.3 equals negative. Again, negative sign. Activation energy over R. This is the value of R, the gas constant R. And then 1 over T2 minus 1 over T1. Make sure that you plug in the numbers in the right place. This is my second temperature. This is my first temperature. And then you solve this equation. You just, this is just a very simple equation that contains one variable. So you can just use your calculator to do the calculation. You calculate ln10, that's 2.3, multiply by 8.3. I think you get roughly 20, and then multiply divided by this. You will get E sub a. It's going to be 80,000 joule per mole. But also, I highly encourage you to explore this website, wolframalpha.com. It's free. So I'm going to do this. I'm going to control-click this website. And what you will see is I'm using this website to do the calculation. Alright, so I have ln10 over ln 1.0. Okay, you don't have to type 0.0, but anyway, equals negative activation energy. I'm going to replace activation energy with x, because if you enter E sub a, it may confuse the website. This website is used to do mathematics, so they don't know what E sub a is. So I'm going to just use x for my activation energy. Negative activation energy over R times, again, 1 over 300 minus 1 over 280. So those are my reciprocal temperatures, all right? 1 over T2 minus 1 over T1. Again, don't put units in here because this is for you to do numerical calculations. I'm going to click the equal sign here. If you click the equal sign, it's going to compute this thing, and it will give you the result. Okay, again, x is 80,000. Okay, there's no unit, but we know it's going to be the SI unit. The SI unit for activation energy is joule per mole. So in the end, we got this 80,000 joule per mole or this 80 kilojoule per mole. All right.